a quiet archive record. Tonight, we drift into the space beneath thought, where words slow down and silence begins to speak. Quantum computing is often described as a new kind of machine, but it is really a new way to use the rules of physics to process information. Ordinary computers store bits that are either 0 or 1. Quantum computers store quantum bits, or qubits, that can behave like 0 and 1 at the same time in a controlled way, and can be linked together through entanglement. That makes some kinds of calculations possible in fewer steps if the hardware and error correction are good enough. Today, quantum computers are still early and fragile. They suffer from noise, they need careful control, and most useful tasks are still research experiments. But the direction is clear. As qubit counts rise and errors fall, quantum machines will do things that are very hard for classical computers, and they will change how we think about security, chemistry, materials, sensing, and optimization. Tonight, we explore the 10 most powerful things quantum computers will do. To understand what makes a quantum computer different, it helps to start with a simple picture of a normal computer. A normal computer breaks a task into tiny steps. It stores information as bits. Each bit is a tiny switch that is either off or on. When a program runs, it moves bits through logic gates. The gates take some input bits and produce output bits. The machine repeats this process billions of times per second. A quantum computer also uses gates, but its basic unit, the qubit, is not just off or on. A qubit can be in a combination of states, a superposition. When you measure it, you get a definite answer, 0 or 1. But before measurement, the state is a weighted mix. This does not mean it tries every answer in a magical way. It means its state lives in a space that grows very fast as you add more qubits. With 2 qubits, the state needs 4 complex numbers to describe it. With 3 qubits, it needs 8. With 50, it is beyond what most classical computers can store directly. Entanglement adds another layer. Entangled qubits behave as a linked system. Measuring one gives information about the other in a way that cannot be explained by independent local properties. In computing, entanglement allows quantum gates to create correlations that are hard for classical machines to reproduce. But there is a hard catch. Quantum states are delicate. Noise from the environment, control errors, and imperfect measurements all push a quantum computer away from the state you want. This is called decoherence. A qubit that is supposed to hold information for a long time may lose it in microseconds or milliseconds, depending on the technology. So the real story of quantum computing is not just the math. It is the battle against errors. To make large quantum machines work, you need quantum error correction. Error correction spreads logical information across many physical qubits. It detects errors without directly measuring the protected information. It then corrects those errors, again, without destroying the computation. The most important future quantum computers will be those that can run long circuits reliably, with many logical qubits, not just many physical qubits. That is the difference between a demo and a tool. With that in mind, the question becomes, what will quantum computers do when they become practical? The most powerful answers tend to fall into 2 categories. Some tasks are about finding patterns or solutions in a huge search space more efficiently. Other tasks are about simulating nature, especially quantum nature, in a way that classical computers struggle to do. The first powerful thing quantum computers will do is break some of the cryptography that protects the modern digital world. Most of the secure connections people use today depend on public key cryptography. This includes systems like RSA and elliptic curve cryptography. These systems work because certain math problems are easy in one direction and hard in the other. For RSA, multiplying two large prime numbers is easy, but factoring the product back into the primes is hard for classical computers. For elliptic curves, related hard problems involve discrete logarithms. A large enough quantum computer running a quantum algorithm called Shor's algorithm can factor large numbers and solve those discrete log problems much faster than classical computers. That means a future quantum computer could break RSA and many elliptic curve schemes in the sense that it could recover the private key from the public key. This is not a small technical detail. It touches banking, software updates, secure messaging, identity systems, and the trust chain of the internet. But it is also not instant doom. There are two reasons. First, you need a large, fault-tolerant quantum computer to do this at a scale that matters for real-world key sizes. Second, the world can shift to quantum-resistant cryptography, also called post-quantum cryptography. These are new schemes designed to be secure against known quantum attacks. Still, the powerful impact is real. The transition to post-quantum cryptography is a major engineering project. It involves updating protocols, hardware, and legacy systems. It also involves a threat called harvest now, decrypt later. An adversary can record encrypted traffic today and store it. If they can break it later with a quantum computer, they can read the old messages. So for data that must remain secret for decades, the clock is already ticking. A second powerful thing quantum computers will do is push new cryptography in the opposite direction, making new forms of secure communication possible. This sounds like a contradiction, but it is not. Quantum computers threaten some cryptography, but quantum physics also enables a method called quantum key distribution, or QKD. In QKD, two parties can share a secret key using quantum states in a way that reveals eavesdropping. The key idea is that measuring a quantum state generally changes it. If an attacker tries to intercept the signal and measure it, the legitimate users can detect an increased error rate. QKD is not the same as having unbreakable encryption by magic. It still depends on careful implementation. Real systems have imperfections. Devices can leak information in unexpected ways. QKD also has practical limits like distance and the need for trusted nodes or repeaters. But it offers a direction where security is grounded in physics rather than computational hardness. Even beyond QKD, quantum-safe security will include new protocols and new trust systems. It will include better randomness generation, better authentication, and safer key management. In the long view, quantum computing will force a redesign of digital security. Some parts will become weaker, other parts will become stronger. The result will be a new security era. The third powerful thing quantum computers will do is simulate molecules and chemical reactions with far greater accuracy, especially in regimes where classical methods struggle. Chemistry is quantum at its base. Electrons live in orbitals, bonds form through quantum interactions, and reaction pathways depend on quantum energy levels. Classical computers can simulate chemistry, but exact simulation scales badly. The wave function of a system of many electrons becomes too complex to track exactly. Because quantum computers naturally represent quantum states, they are well suited to simulate certain quantum systems. The dream is that a quantum computer could compute properties of molecules that are hard to calculate classically. This includes ground state energies, excited states, reaction barriers, and interaction energies. If this becomes practical, it changes drug discovery, it changes catalysis, it changes battery chemistry, it changes fertilizer production, it changes materials for solar cells. Consider drug discovery. Many drug candidates fail because they bind poorly, or because they bind in unexpected ways that cause side effects. Better simulation could reduce the search time and cost. It could also help design molecules that target specific proteins more cleanly. Consider catalysis. Many industrial processes rely on catalysts. Catalysts speed up reactions without being consumed. But finding good catalysts is hard. It often involves trial and error. Better quantum simulation could help design catalysts that reduce energy use, reduce waste, and enable new reaction pathways. Consider batteries. Better batteries require new materials that store more energy, charge faster, and last longer. That often depends on how ions move through a material and how electrons behave. These are quantum problems. A quantum computer will not replace lab work. It will guide it. It will narrow the search. The fourth powerful thing quantum computers will do is help discover new materials with properties that are rare, subtle, or hard to predict. Materials science is full of problems where small changes create big effects. A tiny change in crystal structure can change conductivity. A small change in composition can change strength. Some of the most valuable materials are those that do something unusual. Superconductors, topological insulators, special magnets, and complex alloys. Classical simulation works well for some materials, but for strongly correlated systems where many electrons interact in complicated ways, classical methods often rely on approximations. Sometimes those approximations miss the most important effects. Quantum computers could improve this. They could simulate strongly correlated electron systems more directly. That could help in the search for new superconductors, including the long-sought goal of superconductors that work at higher temperatures and easier conditions. If superconductors become more practical, they change power grids, magnetic systems, and certain kinds of sensors. They reduce energy loss. They allow stronger magnets for medical imaging and research. They enable new device designs. Quantum simulation could also help design lighter and stronger structural materials, better coatings, better semiconductors, and better photonic materials. The fifth powerful thing quantum computers will do is speed up certain kinds of optimization problems that appear everywhere in the real world. Optimization is about choosing the best option out of many. The options can be huge in number. A logistics company wants to plan routes for thousands of deliveries. A factory wants to schedule tasks on machines. A financial system wants to optimize a portfolio under risk constraints. A power grid wants to balance supply and demand while avoiding overload. Many optimization problems are hard because they have many variables and constraints. Some are in the class called NP hard, meaning that the number of possibilities grows so fast that brute force search is impossible. Quantum computers offer several approaches. One is quantum annealing, which tries to find low-energy solutions to an optimization problem mapped onto a physical system. Another is gate-based algorithms like QAOA, the quantum approximate optimization algorithm, which uses a quantum circuit to prepare a state that is likely to encode a good solution. It is still debated how much advantage quantum optimization will provide on real, practical problems. Some problems might not see a clear speed-up. Others might. But even modest improvements can matter. Saving a few percent in fuel use across a global shipping network is a big deal. Improving scheduling in a factory can raise output. Better traffic optimization can reduce congestion. In the near term, hybrid approaches are likely, where a classical computer runs the overall system and a quantum processor is used as a subroutine. The sixth powerful thing quantum computers will do is accelerate machine learning in specific areas and help train or analyze models that are hard for classical systems. Machine learning today is dominated by classical compute. It runs on GPUs and specialized hardware. But there are parts of machine learning that involve high-dimensional linear algebra, sampling, and optimization. Quantum algorithms can, in theory, speed up some of these tasks. There is a lot of hype here. Many proposed quantum machine learning algorithms assume data access in ways that are not realistic, or they hide the cost of loading data into quantum states. Still, there are real places where quantum methods could help. Quantum sampling could help with certain probabilistic models. Quantum kernels could help with classification in some structured problems. Quantum methods might help in generating certain kinds of distributions. Another important angle is that quantum computers can generate data. They can simulate quantum systems and produce outputs that can be used to train models. For example, if you want to train a model to predict properties of molecules, quantum simulation could generate better training data in regimes where classical simulation is weak. So the most powerful impact may not be that quantum computers replace GPUs. It may be that they add new capabilities and data sources. The seventh powerful thing quantum computers will do is improve precision sensing and measurement, even outside of pure computing tasks. This is less discussed in public, but it is a major area. Quantum systems can be extremely sensitive to fields, time, and motion. By using quantum states carefully, you can measure things with high precision. Quantum sensors already exist in forms like atomic clocks. The best atomic clocks are so precise that they can measure tiny differences in gravitational potential, which means they can detect altitude differences. That is not science fiction. It is already here. As quantum technologies improve, sensors can become better at detecting magnetic fields, electric fields, acceleration, and rotation. That can change navigation. It can change geology. It can change medical imaging. For example, quantum magnetometers can detect very small magnetic signals, which could help in brain imaging or heart monitoring. Quantum gravimeters can detect density changes underground, which can help in finding water, minerals, or cavities. In navigation, if you have extremely stable clocks and precise inertial sensors, you can navigate without relying on GPS signals. That is valuable in environments where GPS is weak or can be disrupted. Quantum computers and quantum sensors are related because they use similar hardware and control methods. Improvements in one area can feed the other. The eighth powerful thing quantum computers will do is enable new ways to model complex systems in physics, climate, and high-energy science. Not every complex system is a quantum system. Climate is mostly classical in its large-scale behavior, but some parts of modeling, such as turbulence and certain statistical problems, involve huge state spaces. Quantum computing may help with certain kinds of simulation and sampling. It may help with Monte Carlo methods, which are used in physics and finance to estimate outcomes by random sampling. Quantum algorithms can, in theory, speed up some Monte Carlo tasks. In high-energy physics, quantum simulation could help model particle interactions and quantum field theories. This is still far from practical, but it is a clear research direction. In materials under extreme conditions, like in planetary interiors, quantum simulation could help understand phases of matter. In climate-related work, quantum computing might help with optimization and uncertainty estimation, rather than directly simulating the full climate. For example, it could help optimize energy systems, or help run large ensembles of models more efficiently using advanced sampling. The ninth powerful thing quantum computers will do is change how we design and test complex engineered systems, from aircraft to chips, by improving certain parts of the computation pipeline. Engineering design is full of trade-offs. You want strength, but low weight. You want speed, but low power. You want reliability, but low cost. Design often involves solving large sets of equations, optimizing shapes, and exploring a design space. Classical tools like finite element analysis and computational fluid dynamics are strong, but they can be expensive. Quantum computing could help in sub-problems, such as solving certain linear systems more efficiently, or improving optimization steps. Again, it may be hybrid. In chip design, the challenge is not just physics. It is also constraint satisfaction, routing, and placement. These are optimization problems. If quantum methods help even a little, the impact could be real. In aerospace design, route planning, scheduling, and materials are key. Quantum methods could touch all three. The 10th powerful thing quantum computers will do is reshape the idea of what is computationally feasible, forcing new thinking in science, industry, and policy. This is the most general, but it may be the deepest. Every era of computing changes what people try to do. When classical computers became common, people began to model systems that were once impossible to model. When GPUs enabled deep learning, people began to build models with billions of parameters. When quantum computers become reliable, people will ask different questions. They will attempt computations that were previously out of reach. They will treat certain kinds of simulation as normal. This also changes competition between nations and companies. It changes what needs to be protected. It changes what needs to be shared. It may also change the meaning of trust in digital systems. If old cryptography can be broken, then trust must be rebuilt with new tools. At this point, it helps to separate the near term from the long term. In the near term, quantum computers are likely to be specialized and limited. They will be used in labs and in certain high-value tasks. They will be accessed through cloud services. Many tasks will remain classical. In the long term, if fault-tolerant quantum computers become common, their use will spread. But there is also a possibility that quantum computers remain limited. Not every theoretical advantage becomes a practical tool. The engineering might be too hard. The cost might be too high. The benefits might be narrow. So when people say quantum computers will do everything, that is not accurate. The better statement is that quantum computers will excel in certain tasks where quantum effects or certain math structures matter. The cryptography story is one of the best examples because it is clear and specific. Shor's algorithm is a known tool. The challenge is engineering. The security community is already preparing. The chemistry story is another strong example because it matches the natural strength of quantum machines. A quantum computer does not need to pretend to be quantum. It is quantum. Optimization and machine learning are more uncertain, but they are still important because they are everywhere. Now we can go deeper, moving from the list of powerful outcomes into the mechanics of how those outcomes happen. Consider what it takes to break RSA. You need enough logical qubits to represent the numbers involved, and enough logical gate operations to run the algorithm. You also need error correction strong enough that errors do not drown the result. That implies millions of physical qubits for a machine that can break real keys, depending on hardware and error rates. This is why the threat is not tomorrow for most users. But it is also why the transition should not wait for the last moment. Large infrastructures move slowly. Now consider chemistry simulation. There are quantum algorithms like the variational quantum eigensolver, VQE, which uses a quantum computer to prepare states and a classical computer to adjust parameters. There are also phase estimation methods that can be more precise but require deeper circuits. The early useful quantum chemistry tasks may be narrow. They may involve medium-sized molecules or parts of reactions that are hard. Over time, as hardware improves, the size and accuracy will improve. There is a similar pattern in materials science. Early results will likely be about specific model systems. Then they will connect to real materials. Now consider optimization. Many real optimization problems include noise, uncertainty, and changing conditions. They are not clean math puzzles. A quantum method that gives a theoretical speed-up on a clean problem might not help on a messy real one. So the most successful quantum optimization tools may be those that fit into real pipelines, and those that can be tuned to specific classes of problems. Now consider machine learning. One key barrier is data loading. A quantum algorithm may assume that you can load a large vector into a quantum state quickly, but that is not free. You need a process that sets the amplitudes of a quantum state. That can be as hard as reading the data. So a useful quantum machine learning approach may avoid large data loading. It may focus on smaller structured data sets, or on generating data, or on using quantum processors in a way that does not require full amplitude encoding. Now consider sensing. Quantum sensing is powerful because quantum states can carry phase information with high precision. In an atomic clock, the frequency of an atomic transition is used as a reference. In an interferometer, quantum phases can be measured to detect motion or fields. Better clocks and sensors are not just scientific tools. They are infrastructure. They affect telecommunications. They affect finance, where time stamps matter. They affect navigation and defense. So even if a quantum computer remains hard, the surrounding quantum technology can still have big impact. At this point, it is worth stating a simple truth. Quantum computing is not one technology. There are multiple ways to build qubits. Some use superconducting circuits. Some use trapped ions. Some use neutral atoms. Some use photons. Some use spins in semiconductors. Each approach has trade-offs. Superconducting qubits are fast and have strong engineering progress, but they need cold temperatures. Trapped ions have long coherence times and high gate fidelity, but they can be slower. Neutral atoms can scale in arrays, but controlling interactions is complex. Photonic approaches can operate at room temperature, but building deterministic gates is hard. It is possible that one approach will dominate. It is also possible that different approaches will serve different tasks. The central requirement remains the same: low error rates, scalable control, and fault tolerance. Now we return to the theme of the episode: the 10 most powerful things quantum computers will do. We can restate them as a single arc. They will force a shift in cryptography, breaking some old methods and pushing new ones. They will enable chemistry and materials simulation that guides real industrial discovery. They will improve optimization in logistics, energy, and finance, at least for some classes of problems. They will add new capabilities to machine learning, especially through sampling and through better simulation data. They will improve sensing, clocks, and navigation. They will open new doors in physics simulation. They will change engineering design pipelines, and they will reshape what seems possible. Now, to keep the story grounded, it helps to ask, what are the constraints and risks? One risk is overhype. If people promise that quantum computers will solve every hard problem, the field can suffer when reality is slower. The history of technology includes many hype cycles. Another risk is uneven benefit. Powerful tools can widen gaps. Organizations with access to quantum hardware and talent may gain advantage. This is true for any advanced technology. Another risk is security transition failure. If post-quantum cryptography rollout is slow or incomplete, some systems may remain vulnerable. Legacy devices can persist for decades. There are also risks in the quantum ecosystem itself. Supply chains for cryogenic systems, lasers, and specialized materials may become strategic. But there are also clear benefits. Better catalysts can reduce emissions. Better batteries can improve energy storage. Better sensors can improve safety. The path from research to impact will likely have phases. Phase 1 is demonstration. Quantum computers show that they can do small tasks reliably and that error correction works. Phase 2 is early practical use. Quantum machines provide advantage in narrow tasks, often in research settings. Phase 3 is broader integration. Quantum processors become part of general compute infrastructure. We are currently moving from Phase 1 to Phase 2, depending on the domain. Now consider a deeper question. Why is simulating chemistry so hard for classical machines? The core reason is that quantum systems have an exponential complexity in the worst case. If you have a system of many electrons, the number of possible configurations grows rapidly. Classical methods compress the problem with approximations. These approximations often work, but not always. Quantum computers can represent the state more directly. They still need careful algorithms, but the mapping is more natural. This is why chemistry and materials are often seen as the most realistic, near-term quantum advantage area. Now consider another deep question. Why does Shor's algorithm matter so much? Because it is a clear example where a quantum algorithm gives a large speed up, from sub-exponential to polynomial time for factoring. It hits a real-world system that people care about. This is why post-quantum cryptography is a major topic. Now consider the role of error correction. Error correction requires redundancy. It can turn a noisy physical qubit into a more stable, logical qubit. But the overhead is large. That means early quantum computers will be limited. They may have many physical qubits, but only a small number of logical qubits. As hardware improves, the overhead drops, so the growth curve may not be smooth. It may have jumps. There may be a moment when error correction becomes practical at scale, and then capabilities rise quickly. Now consider one more powerful outcome that does not fit neatly into one category: quantum communication networks. If quantum repeaters and quantum memory become practical, it may be possible to build a quantum internet, a network that can distribute entanglement across long distances. This could enable distributed quantum computing, where small quantum processors work together. It could also enable new cryptographic protocols. Again, it is engineering heavy, but it is a real direction. Now we can shift into a more narrative exploration of each of the 10 outcomes, with examples. Imagine a future company that designs catalysts for green ammonia production. Ammonia is used for fertilizer. Today, making ammonia is energy intensive and produces emissions. A better catalyst could reduce energy use. A quantum computer could simulate candidate catalysts and reaction pathways. It could identify which structures lower the energy barrier. The lab could then test a smaller set of candidates. This could speed up progress. Imagine a future battery lab. The team wants a solid-state electrolyte that allows fast ion movement but is stable and safe. The chemistry is complex. The structure is subtle. A quantum computer could help predict which crystal structures will have the right pathways for ions. Again, the lab tests fewer options. Now imagine a future logistics system for a city. The city wants to route electric delivery vehicles. It must consider traffic, charging stations, time windows, and vehicle limits. A hybrid quantum classical optimizer might find slightly better routes than a classical heuristic. Even a small improvement can reduce costs. Now imagine a future financial system that runs large risk models. Some parts of risk estimation use Monte Carlo simulation. Quantum speedups for Monte Carlo could reduce compute time. This could allow more scenarios. Now imagine a future scientific lab trying to understand a complex material under pressure, like hydrogen-rich compounds that might superconduct. Quantum simulation could help predict phase diagrams. Now imagine a navigation system that must work without GPS. A combination of quantum clocks and inertial sensors could allow precise navigation. Now imagine a medical device that uses a quantum sensor to detect tiny magnetic signals. That could improve imaging. These are not guaranteed outcomes, but they are plausible targets. Now, it is also useful to consider what quantum computers will not do. They will not automatically make every computation faster. Many tasks are already efficient classically. They will not solve NP-hard problems in general in a way that makes every hard problem easy. There is no evidence that quantum computers can do that. They will not remove the need for good data, good models, and good experiments. They will not replace human judgment. So the correct way to think about quantum computers is as a new tool with specific strengths. Now we move toward the ending. We will tie the 10 powerful outcomes into a single closing view. Quantum computers will likely arrive in the world in a quiet way. They will not show up as a single day when everything changes. They will appear as small wins in labs, then as specialized services, then as integrated tools. The most visible change for most people may be the cryptography transition. People may notice software updates that change encryption. They may not even know why. The deeper change may be in science and industry. Better simulation can lead to better products. So the most powerful things quantum computers will do may not be visible as quantum computing. They will be visible as better medicine, better materials, better energy systems, and a safer, more robust digital world. And the shift will also teach something about reality. Quantum computing is one of the clearest examples of an idea that is both abstract and physical. It is built on math, but it is grounded in hardware, in noise, in temperature, in control. It is a reminder that information is not separate from physics. It is written into matter. It is shaped by the laws that govern the universe. To make that reminder concrete, picture the inside of a modern quantum lab. It does not look like a glowing cube from a movie. It looks like a careful industrial instrument. In one common approach, a quantum processor sits inside a dilution refrigerator, a tall metal cylinder full of layered plates and wiring. The refrigerator cools the device to temperatures close to absolute zero. At those temperatures, certain metals become superconducting and can form qubits that behave like tiny quantum circuits. There are coax cables and filters. There are microwave generators. There are amplifiers designed to preserve weak signals. The lab is full of small details that matter. A small vibration, a bad connection, or a stray electromagnetic signal can change the results. This is why the future of quantum computing is not only a story about algorithms, it is also a story about manufacturing, materials, control systems, and calibration. When people say the power of a quantum computer grows exponentially with the number of qubits, they are describing the size of the state space. But they are not saying that every problem becomes easy. The real power comes when a quantum algorithm can steer that huge state space toward the answer you want, and when the machine can do it without losing the information to noise. So each of the 10 powerful things quantum computers will do has a hidden second part. The hidden part is the path to making it reliable. Return to the first outcome, breaking certain public key systems. The reason this is such a defining effect is that public key systems are baked into almost everything. When your browser connects to a website, it uses a handshake that depends on public keys. When software updates are signed, the signatures depend on public keys. When a company issues an identity credential, it often relies on public keys. The breaking event is not only about reading secret messages, it is also about forging trust. If an attacker can break the signature scheme that authenticates updates, they can make fake updates look real. If they can break the keys that protect an identity system, they can impersonate people. So the long-term response is not only switching algorithms, it is also improving the way keys are rotated, stored, and audited. One of the strange features of this transition is that it is mostly invisible when it is done well. If a major platform silently moves from elliptic curve signatures to a post-quantum signature scheme, most users will not notice. They will still click and connect. But under the surface, the math is different. The second outcome, quantum key distribution and physics-grounded security, is often misunderstood. QKD does not prevent all attacks. If an attacker can break into an endpoint device, QKD will not save you. If the implementation leaks side channel information, QKD will not save you. But QKD can protect the channel in a strong way, and that matters in certain settings. In a future where post-quantum crypto is standard for most internet traffic, QKD may still matter for high-security links, for critical infrastructure, and for certain government and scientific networks. Now, shift to chemistry, the third outcome, and slow down inside it. When a chemist wants to predict a reaction, they want to know the energy landscape. They want to know which states are stable, which are unstable, and which paths are accessible. Even if you have a good intuition, the details can surprise you. A molecule can have a shape that flips. A solvent can change the outcome. A tiny change in substituent can change the whole pathway. Classical chemistry simulation has built a powerful toolkit. It includes density functional theory, coupled cluster methods, and many approximate models. These methods have enabled real progress, but they have limits. Some systems are so strongly correlated that classical approximations fail. Some reactions are too large to simulate accurately. A useful quantum computer would not solve all of chemistry overnight. It would start by providing reliable results for specific hard subproblems. Then it would expand. One practical picture is that quantum simulation becomes a filter. A lab may generate thousands of candidate molecules with a classical model. Then it uses a quantum computer to simulate the most promising candidates more accurately. It does not replace the search. It sharpens it. The fourth outcome, materials discovery, follows a similar pattern. Materials are often chosen by screening. You test composition, structure, and processing. You see what happens. Many of the most important discoveries have been partially accidental. A future quantum tool could reduce the accident part. It could predict which materials have desirable properties before you make them. It could also explain why a certain structure works, which helps you improve it. Now consider superconductors again, because they are a good example of a difficult material problem. Superconductors carry electric current with no resistance, but most superconductors require very cold temperatures. Some materials have shown superconductivity at higher temperatures under extreme pressure. People are searching for materials that do it at easier conditions. The problem is that superconductivity is deeply tied to quantum interactions in a material. In some cases, it can be modeled with approximations. In others, it is part of the hard zone of strongly correlated physics. A quantum simulator that can model these interactions could help identify candidates that classical models miss. Now, the fifth outcome, optimization, can be made more real by thinking about how many optimization problems hide inside daily systems. A delivery fleet has to decide which package goes in which vehicle, which route the vehicle takes, and which time windows it must hit. Each choice affects the next. Weather changes traffic. Accidents change routes. A classical optimizer can handle this with heuristics and machine learning. A quantum optimizer might not replace the whole system. It might act as a solver for the hardest part, like a combinatorial core. It might be called repeatedly as conditions change. The reason this can matter is not only speed, it is also the ability to explore a wider range of options. If your solver can look deeper into the choice space, it can sometimes find solutions that are hard to reach with classical heuristics. The question, of course, is whether quantum methods will reliably beat classical ones on real instances. That is not guaranteed. It will depend on the structure of the problem and the quality of the implementation. But even if quantum methods do not win broadly, they can still win in niches. Now, the sixth outcome, machine learning, can also be grounded. There are two separate ideas people mix together. One is using quantum computers to speed up parts of machine learning. The other is using machine learning to control quantum computers and find better quantum circuits. The second is already happening. Running a quantum machine requires constant calibration. Machine learning can help choose control parameters, correct drift, and diagnose errors. The first idea, quantum machine learning, is still uncertain, but it has plausible paths. One path is quantum-enhanced sampling. Many machine learning models rely on sampling from a complex distribution. If a quantum device can sample more efficiently in certain cases, it could speed up training. Another path is that quantum models can represent certain distributions naturally. If your data has a quantum origin, like outcomes from quantum chemistry or quantum sensors, a quantum model could match it better. Even if the ultimate machine learning advantage remains unclear, quantum computers will likely become part of the machine learning ecosystem by providing simulation data, by enabling new features, and by shaping security assumptions. Now, the seventh outcome, sensing, is a quiet kind of power because it improves perception. If you can measure magnetic fields with higher precision, you can see underground features without digging. You can detect failures in machines before they break. You can see biological signals with less noise. If you can measure time with higher precision, you can synchronize networks better. You can locate things more accurately. You can compare clocks across the Earth and see gravitational differences. This kind of power does not look like a big headline, but it accumulates. Now, the eighth outcome, modeling complex systems and improving sampling, is subtle, so it helps to be specific. Monte Carlo simulation is widely used because it turns a hard integral into repeated random sampling. You can estimate the value of an option or a risk measure or a physical quantity by sampling many scenarios. Quantum algorithms can, in theory, provide a quadratic speedup for some Monte Carlo tasks. A quadratic speedup sounds modest, but it can be large in practice because Monte Carlo often uses huge sample counts. If you can cut the sample count from 1 trillion to 1 billion, that matters, even if it is not a magical exponential improvement. The ninth outcome, improved engineering design pipelines, is where many modest improvements can add up. Design is often iterative. You propose a design, simulate it, adjust it, simulate again. If each simulation step is expensive, progress is slow. If quantum methods reduce the cost of certain steps, you can explore more designs. In chemical engineering, this overlaps with catalyst design and process optimization. In electrical engineering, it overlaps with chip placement and routing. In mechanical engineering, it overlaps with scheduling and materials. And the 10th outcome, reshaping what seems feasible, is the broad consequence of the first 9. When a tool changes what is easy, it changes what people attempt. Now, because the title of the episode mentions 10 powerful things, it is worth tracing through them in a more deliberate way, without turning the story into a list of bullet points. First, there is the direct cryptography impact. the breaking of certain public key schemes. Second, there is the security redesign, including post-quantum cryptography and quantum-enabled key distribution. Third, there is quantum chemistry simulation, which feeds drug discovery. Fourth, there is materials discovery, including superconductors and complex electron systems. Fifth, there is optimization, which feeds logistics, scheduling, and energy. Sixth, there is machine learning acceleration and new model types, and machine learning used to control quantum hardware. Seventh, there is precision sensing and timing. Eighth, there is improved simulation and sampling in physics and other fields. Ninth, there is improved engineering design pipelines. 10th, there is the broad shift in what research and industry can attempt. Even stated this way, the core is still the same. Quantum computers will be powerful because they will let us compute in a way that matches the underlying physics of certain problems. Now consider a question that often appears. Why not just build bigger classical computers? The short answer is that classical computers are very good, but some problems scale too fast. You can add more hardware, but you still hit exponential growth in memory or time. For some quantum systems, classical simulation becomes impossible at moderate size. This is why quantum simulation is so compelling. It is also why early claims of quantum advantage often focus on sampling tasks that are hard to simulate classically. But the word advantage matters. A quantum machine can do something a classical machine cannot do in reasonable time. But if that task is not useful, it is not a revolution. The real revolution is when the advantage hits a useful problem. That is why the chemistry and materials track is so important. Now shift into another part of the story, the part about error correction and scale. A good way to picture quantum error correction is to picture a message written across many fragile carriers. Each carrier can flip or lose information. If the message is written with redundancy and structure, you can detect which carriers are wrong and reconstruct the intended message. In classical error correction, you can copy bits freely. In quantum error correction, you cannot copy an unknown quantum state. This is the no cloning principle. So quantum error correction has to be clever. It measures certain properties of the system that reveal errors without revealing the protected data. One popular family of error correction codes is called surface codes. They arrange qubits on a grid and measure checks that detect errors. Surface codes have favorable thresholds, meaning that if your physical error rate is below a certain level, you can make the logical error rate exponentially small by using more qubits. The cost is overhead. A single logical qubit may require many physical qubits. So the timeline of quantum power depends on when error correction becomes practical. As hardware improves, the overhead drops. Logical qubits become cheaper. This is why progress can feel slow for a while and then speed up. Now, to make the arc feel more like a documentary and less like a lecture, it helps to tie quantum computing to a familiar theme, the history of tools. A tool begins as an experiment. It becomes a specialized instrument. It becomes a platform. Then it becomes invisible infrastructure. Classical computing followed this path. Electricity followed this path. The internet followed this path. Quantum computing is likely to follow the same path. In the experiment stage, you care about demonstrating that a qubit works. In the specialized instrument stage, you care about demonstrating a narrow advantage. In the platform stage, You care about software stacks, compilers, and user access. In the infrastructure stage, most people do not think about it. They just benefit from it. Now, imagine a future day, years from now, when a researcher wants to design a new antiviral drug quickly during an outbreak. The researcher starts with a protein structure. They want to find a molecule that binds to it. They use classical methods to generate candidates. Then they run a high-accuracy simulation on a quantum machine for the top candidates, focusing on binding energy and conformational states. This does not give a perfect answer, but it reduces uncertainty. The lab tests fewer candidates. The time to find a useful drug goes down. This is the kind of quiet win that would matter. Now imagine a future power grid operator trying to integrate renewable sources. The grid has many inputs: solar, wind, storage, demand response. The problem is dynamic. They use classical control systems, but the planning step, the day-ahead optimization, is huge. A quantum-assisted optimizer might help search the space of possible schedules more efficiently. Again, maybe it gives a few percent improvement. A few percent can be big. Now imagine a future factory that runs a complex supply chain. Materials arrive, machines need maintenance, schedules shift. Optimization is constant. Even if quantum advantage is limited, any improvement in scheduling can reduce downtime. Now consider another branch of quantum impact that is often missed: the impact on standards and governance. When cryptography changes, standards bodies change. When standards change, compliance changes. When compliance changes, industries change. So a quantum shift can ripple outward into regulation, auditing, and legal frameworks. This is why governments pay attention. Now consider a more philosophical point. Quantum computing is sometimes described as a new kind of parallelism, but the better view is that it is a new kind of interference. A quantum algorithm sets up amplitudes and uses interference to amplify the right answers and cancel the wrong ones. This is a strange kind of computation. It feels more like wave physics than like logic, and it is a reminder that nature itself is not digital in the simple way we often imagine. At the smallest scales, it is probabilistic and wave-like. Now, because the title uses the phrase "most powerful things," it is worth clarifying what powerful means. Powerful can mean fast. It can mean precise. It can mean enabling something that was not possible. Breaking RSA is powerful because it changes trust. Simulating molecules is powerful because it changes discovery. Optimization is powerful because it changes efficiency. Sensing is powerful because it changes perception. And the broad shift is powerful because it changes what questions can be asked. Now we can also ground the topic by acknowledging uncertainty. It is possible that quantum computers will remain expensive and rare. It is possible that their main use will be in high-value research and government work. It is possible that classical computers will adapt and reduce the advantage. In fact, classical simulation methods improve when a new threat appears. Researchers find new approximations. They find new compression methods. They use better hardware. So the gap between quantum and classical can move. But even with these uncertainties, the direction of the most likely impacts remains. Cryptography must adapt. Chemistry and materials research will gain new tools. Certain optimization and sampling tasks may improve. Sensing will improve. Now, shift into a final closing that ties the whole story into a quiet conclusion. The most powerful quantum computers of the future will not look like a single dramatic device. They will look like a new layer in the world. They will sit behind research, behind security, behind design. They will be part of a pipeline. They will be called when needed and ignored when not. And what they will really do is widen the boundary of what can be computed. In the domains where the world itself is quantum, there is also a quieter consequence that follows from all of this. When a new tool appears, it changes education and it changes what skills are valued. A world with reliable quantum machines will need people who can think across physics, math, and engineering. It will need people who understand noise, error budgets, and control systems. It will need people who can turn a scientific question into a circuit and interpret the output with care. In the early years, quantum computing will likely remain a specialized field. But over time, the concepts can spread the way classical computing concepts spread. Most software developers do not design transistors, but they still use abstractions that rest on transistor behavior. In the same way, most future developers may not design qubits, but they may use quantum modules as part of a larger system. This is another reason the most powerful impacts may be indirect. The chemistry expert may not become a quantum physicist, but they may use a chemistry tool that contains a quantum backend. The logistics expert may not know the details of QAOA, but their solver may have a quantum option when the instance is hard. The security engineer may not care about qubit gates, but they will care about certificates and key rotation. This indirect path is common for technology. The tool becomes part of the environment. Now consider one last example that ties several of the 10 outcomes together. Imagine a company building a new kind of refrigeration system for large data centers. The goal is to reduce energy use. The challenge is selecting a working fluid, designing a cycle, choosing materials for heat exchangers, and optimizing control. Chemistry matters because the working fluid must have the right properties. Materials matter because the heat exchangers must conduct heat well, resist corrosion, and be cheap enough. Optimization matters because the cycle must be tuned for different external temperatures and loads. Sensing matters because you need precise monitoring. Security matters because the control network must be protected. In that kind of engineering problem, a quantum computer could appear in the background. It could help simulate a new material coating. It could help screen a chemical candidate. It could help optimize a schedule for load balancing. No single piece is dramatic, but together they change the outcome. That is a realistic way to think about quantum power. It is not a lightning strike that replaces everything. It is a set of advantages that attach themselves to hard parts of real workflows. Now, there is another question that helps keep the story honest. Why are we confident that quantum computers will do any of this if the hardware is still so limited? The reason is that the underlying physics is not in doubt. Superposition and entanglement are not speculative. They have been tested in many experiments. The algorithms that show large speedups are not vague ideas. They are well-defined procedures. What is uncertain is the engineering. How fast will error rates improve? How cheaply can qubits be manufactured? How stable can control be made? How quickly can software stacks mature? How well can these systems be integrated into real applications? Some problems may turn out to be harder than expected. For instance, scaling control wiring and reducing crosstalk can be difficult. maintaining calibration across large devices is difficult. Building quantum memory with long lifetime is difficult. Creating quantum repeaters for long-distance networks is difficult. But the field has a pattern. Each year, small improvements compound, and the timeline does not have to be short for the impacts to be real. Cryptography transition is already underway. Research groups already use quantum processors for experiments. Industry already invests because the potential return is large. In other words, the future is being built slowly, while the machines are still small. At the end of the story, the simplest statement may be the most accurate. Quantum computers will be powerful because they are built from the same rules that make molecules, materials, and light behave the way they do. They will change security because they change what math is hard. They will change science because they change what simulation is possible. They will change engineering because they change what can be optimized. They will change measurement because they change what can be sensed. And once those changes arrive, the question will no longer be whether quantum computers matter. The question will be which parts of the world changed first and which changed later. One more quiet part of the topic is the way quantum computing forces people to think about limits. A classical computer is limited by heat, by transistor density, and by energy cost. But for many everyday problems, those limits feel far away. You can rent more servers. You can compress data. You can change the algorithm. Quantum computing puts a different kind of limit in the foreground. It makes the limit of simulation feel immediate. It shows that even if you have infinite classical hardware, some direct representations of a quantum state will still be too large. This does not mean the universe is unknowable. It means we need better tools and better abstractions. It also means that some of the strongest uses of quantum computers will be those that let us answer a narrow question without simulating everything. For example, in chemistry, you may not need a full wave function. You may only need a reaction barrier or a binding energy. A quantum algorithm can be designed to estimate exactly that. In optimization, you may not need the perfect global optimum. You may only need a solution that is better than the current one under time pressure. Quantum approximate algorithms fit that mindset. In security, you may not need to break every scheme. You may only need to defend against the best realistic attacker. That is why post-quantum standards focus on practical threat models. This idea of targeted answers matters because it shows how quantum computers will likely be used in practice. They will not be used as general-purpose machines that run every kind of program. They will be used as specialized instruments for high-value parts of a workflow. Another part of the future is the software layer. Today, most people who write programs do not manage memory bits directly. They use languages, libraries, and compilers. The same is beginning to happen for quantum computing. People write circuits in high-level forms. Compilers map them to hardware gates. Error mitigation and error correction layers sit underneath. As this software stack improves, it becomes easier to apply quantum methods to real problems. That does not guarantee advantage, but it changes accessibility, and accessibility changes experimentation. In the early classical computing era, a small number of experts could use computers. Over time, more people could. The result was not only more users, it was more ideas, more applications, and faster feedback. quantum computing could follow a similar path. Now, end with one last image that fits the tone of the topic. Think of a quantum computer as a careful, quiet machine that holds fragile patterns long enough to let them interfere. Those patterns encode a question. The interference encodes an answer. The machine does not shout. It only returns a set of probabilities. But inside those probabilities can be information that was unreachable before. That is why the 10 most powerful things quantum computers will do are not a single trick. They are a set of new ways to ask nature for its answers, and to do it with less guesswork. If the story has a final practical takeaway, it is this. The shift is not only technical, it is organizational. Companies and governments that prepare early for post-quantum security will avoid emergency upgrades later. Research teams that learn how to combine quantum tools with classical workflows will be ready to use advantage when it arrives. Engineers who treat quantum computing as a part of a larger system rather than a replacement for everything will build the best applications. And anyone who watches the field should watch the same indicators. Logical qubits, not just physical qubits. Error rates, not just device count. Algorithm depth that can be sustained. Practical benchmarks tied to chemistry, materials, and optimization, not only abstract demos. Those indicators are the difference between a lab curiosity and a working tool. Over time, the machines will grow quieter, in a sense. They will become more stable. They will need less constant tuning. They will move from fragile experiments to robust instruments. And when that happens, the most powerful thing they may do is the simplest. They will turn problems that used to be guesswork into problems that can be computed, tested, and repeated. There is a quiet irony here. For decades, the word quantum sounded like something distant from daily life. But the effects of quantum computing will show up in ordinary places. In the certificates that secure a website. In the way a phone updates its software. In the materials inside a battery. In the catalysts inside a chemical plant. In the sensors that help a ship or aircraft navigate. Most people will not call these effects quantum. They will call them faster, safer, cheaper, more reliable. And in the background, the machines that made those improvements possible will continue to sit in controlled rooms, cold or precisely trapped or carefully lit, holding fragile states long enough to let interference do work. In that sense, quantum computing is not only about speed, it is about reach. It reaches into parts of reality that classical models can only approximate, and it brings back answers that can be checked against experiments. When those answers start to arrive regularly, the technology will feel less mysterious. It will feel like what it is. Another tool built from physics, used by people, changing the world in quiet increments. And when you look back later, the change will seem obvious, because the results will be everywhere. But from the inside, it will still feel like careful steps, taken one at a time. This was a quiet archive story, where the story ends, sleep begins,